Our next speaker is Karim Adiprasito, who will talk about anisotropy, bias pairings, and the Lefschetz product. Karim?
Yeah, thank you, everyone. I want to talk about. I want to basically give you an intuition of how Lefschetz properties are proved in absence of a geometric structure that we have for varieties. And in particular, I want to kind of sketch the two main proof ideas for you. And so I want to prove Lefschetz. And there's the kind of an almost geometric proof, which kind of uses some geometric manipulations, tricks. And then there's the proof that basically uses a transcendental extension and manipulating just the volume polynomial. So volume polynomial. And interesting identities. Okay. And it turns out that both of these proofs, in the end, they kind of use the same trick. They reduce the Lefschetz property to a pairing property. So idea reduce Lefschetz to a pairing. Right. So I mean, what is a pairing property? I mean, that's maybe oh, sorry, I wanted to have a new page, but I started somewhere in the middle now. That's not okay. Okay. What do I mean by a pairing property? Well, remember that, okay, so what are we looking at, right? We are looking at, in the simplest case, sigma, a triangulated sphere. Okay, and let's not worry for the moment what the characteristic is. We don't care. It's an honest homotopy sphere, let's say. And we're fixing a field K. And for simplicity, let's say that K is infinite. Field. All right. And then we are looking at, let's say this is of dimension d minus 1. And then we are looking at this ring K of sigma, the Stanley Riesen or the phase ring. All right, and then mod out this linear system of parameters that we have now seen several times. What do I mean, this ring here we call A of sigma. And I index this by this little theta because it doesn't only depend this ring A of sigma, it's an Artinian ring, but it doesn't only depend on sigma, it also depends on theta. Okay, so there's some non-trivial information, some non-trivial geometric information contained in this theta. So for instance, in the last talk, we heard about the case when the fan is unimodular. And that, I mean, via this correspondence between fans and polynomial homized polynomial rings. And by the way, these homized polynomial rings are actually just the Chow rings of varieties. These rings are related to these properties are related to properties of theta. So in some way, theta is encoded there, right? So this was in Paul's talk in the morning, and kind of plays in here. That's all. So theta is important. But what do we want, right? So we want the Lefschetz property. And this is, right, we have AI, sigma. and we have AD minus I sigma, right? And we want to, I mean, so these, remember, these here are Poincaré duals, so there's a perfect pairing, right? So I can multiply them and I land in AD, and this pairing is perfect, right? And but what I want is a more direct isomorphism, and this here should be via this L to the D minus 2I, where L in A1 is some element. Okay, and we want this to be an isomorphism somehow as an isomorphism. Okay. And that's it. All right, so that's the Lefschetz property. That's where we want to go. So how do we access that? Well, I said that my pairings are important. So let's not, I mean, we don't know how to construct this Lefschetz property. So instead, let's look at the pairing property, the one that we do understand. So we have AI and AD minus I, and we have this pairing is perfect. Okay, and that's okay. So this is in this is in some sphere for some given I for any I. Okay, this is perfect. Okay, so that's the nice thing. But let's say, okay, so we want what we want, right? Let's say we want the most simple Lefschetz theorem. Let's say we want to have the case when, what is the first non-trivial Lefschetz property? Well, when D is even, right? So D is equal to 2K. No, sorry, that's not true. So if D is equal to 2K, let me do that like this. So, and D minus 1 is equal to 2K. Well, what do we have then? Well, we have the first non-trivial Lefschetz isomorphism that is just in the middle, right? So we have the map from AK to AK plus 1, and we want to have this here. So we want, yeah. So we have this, and we want this. And in some way, we want to relate the two. Okay, so what's the trick? So let me write some symbols here. So sigma and sigma, 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 sigma. So the trick is the following now. Consider the suspension of sigma. All right, this is a D sphere. Is D sphere where D is equal to 2K plus 1. All right. And we want this isomorphism, right? That's the basic. This is the first non-trivial, first Lefschetz. And we want to consider the suspension of sigma, where sigma is the original D minus 1 sphere. So this is a D sphere, right? So suspension again, it looks like this. Okay. That's small. Here's my sigma. Sits here in the middle, and then I suspend, and I get the 1/2. Okay, so let me look at the north pole of this. Okay, So this is n, this is somehow that's the North Pole. It has some, it's associated, there's some associated variable to it. Okay. And of course, in the suspension of sigma, we also have a perfect pairing. Now between degrees, well, the degree I, suspension of sigma, and the degree I plus 1 of the suspension of sigma. Okay. Oh, sorry, that's not true. Between d plus 1 minus I. And this pairing is perfect. My ground field. Okay. So this pairing is perfect. What does it have to do with the original? Here's a claim, and this is kind of the key lemma, or the key observation that is kind of the cornerstone of, if you want, of both papers. So key lemma. So all the proofs that we know of hard Lefschetz, of this hard Lefschetz of the G conjecture for spheres rely on this. The following are equivalent. If I look at the ideal of Xn in, all right, so let me write it small, in a suspension of sigma, and I want to multiply. Okay, so what I want to do is I want to restrict this pairing here to the same space. So a, so this is, what do I want? This is Xn. All right. So now I want to look at this pairing. This is just the restriction of this pairing, and I want to look at it in degree k plus 1, k plus 1, k plus 1. Right. I just look at the degree k plus 1 part. So I mean that means to make clear that this is not the power of the ideal. It's just I restrict to that degree. All right. So pairing in this degree, and this pairing, right, again goes to k. And the statement is that this pairing is non-degenerate. Non-degenerate. Okay, so this is the first point. And the second point is that, so A theta, okay, so theta, okay, so let me write it. So I want to have like okay, so let me do it as follows. So I have to explain a little more. So what is the linear system of parameters here? I have, okay, so I have theta, right? So okay, let me go back a little bit to the last lesson, to the last time I talked. So remember, I could think of these A theta. This theta here was a matrix, right? So theta was a matrix of indeterminates, or yeah, a matrix times this vector of variables. All right, so this was for A theta of sigma. And of course, for the suspension, there's also a theta. All right, but because the dimension is one higher, this linear system of parameters, this must be one element longer. So theta bar is, well, what does it look like? It looks like V delta. But then there is this mysterious additional element added. Let me call it height. Okay, so there's a final element h added. That's x bar. Okay. So I have one more entry. Okay, so let me here, and this is in a theta bar suspension of sigma. And here, what do I want? Well, I have a theta of sigma in degree k, and I have a theta of sigma in degree k plus 1. And these are the two that I want to connect by Lefschetz isomorphism. So let me just put h times this vector of indeterminate. Right? This is a linear form. and this is an isomorphism. That's a claim. Okay. So let me give an idea on how to prove that. But this basically tells you Lefschetz, right, is equivalent to pairing as ideals. All right, that's it. That's the whole observation. That's a key lemma. So let me give the intuition of the proof. So so let's look at this matrix. All right, so let's look at theta bar, because I cheated a little, right? It looks like V delta and then H, right? But it also has two additional columns, right? It has the north column and the south column, right? For these two new vertices. So I have a coordinate for xn and a coordinate for xs. Let me write it. I can just assume that they are one, it doesn't matter. So let me do it like this. All right, so this is how it really looks. And so now let's look at this. Let's look at the spaces here. So I have a theta sigma. All right, I have in degree k. I have a theta sigma in degree k plus 1, and I have this multiplication with h times x. Okay, sorry, h times. Okay. And now what do I want? Well, okay, so note that hx bar is equal to xn plus xs in a theta bar suspension of sigma. So what I do is I can just draw a beautifully simple commutative diagram. And what I have here, okay, so let me multiply. Okay, so h times x, I can multiply with xn plus xs. So I land in xn plus. So I land in the ideal of xn and the ideal of xs. All right. So let's ignore, because in the end we want to only see what is in the North Pole. Let me just restrict to what happens in the North Pole. So what I mapped here is from AK, I map to the open star a star of n in the suspension of sigma to the bound relative to the boundary, the star of n in the suspension of sigma. All right, and this is the multiplication with xn. Okay, so this multiplication elevates the degree by 1, and then I can, okay, so this I can naturally map to ak plus 1 of the star of n in the suspension of sigma. All right, and this here is an isomorphism. This is what you know as this cone lemma. This relation between cone would be between star and link. They give you the same rings. So I have these two spaces, and I get a commutative diagram like this. And okay, so in particular, I have this map here, up here, and it's clear that the isomorphism down here is equivalent to an isomorphism up here. But this here turns out to be, if you think about it, this here is just, okay, this is the ideal of xn. And this here, this part here is the dual of this ideal under the Poincaré pairing. It's a dual to xn under the Poincare pairing. Okay. Now, what does this mean? Well, a map from an ideal to its dual is an isomorphism, is injection if and only if the pairing is non-degenerate. So injection here is equivalent to the pairing being non-degenerate. And that's the proof of the lemma. That's it. Okay, it's just a little bit of homological algebra. And voila, that's the idea. Nothing more to be done. Well, except, okay, so what else? I mean, now, so now what we need to do is we now need to prove. Now we need to prove we need to prove that the pairing at xn does not degenerate. And now the kind of the proofs kind of differ, and the idea is as following. In the original proof of mine, the idea is now idea one. Prove that the pairing does not degenerate at, so pairing does not degenerate at all monomial ideals. And the second idea, and this is this originates beautifully in the work of Stavros Papadakis and Vasiliki Petrotou, and Lasso can, you can, she's around, you can torture her more. That the idea here is that you prove this at all ideals. Pairing does not degenerate anywhere. Okay. Those are the two results. Right. So those are the two key ideas. Unfortunately, for now, we only know how to make this work in characteristic 2. There are some intermediate results that we have that we can do in all characteristics are kind of more general than monomial ideals, but less general than kind of this pairing at all the ideals. All ideals just means at all principal ideals, right? And then it's just anisotropy. Well, this method, the method here on the left is agnostic to the characteristic, and I will try to kind of sketch them both and give you an idea. Okay. So ideas or the key steps, we do it like this. For idea 1, monomial ideals. And let me just say, we can reduce to ideals of the form, okay, so we have our sphere sigma, right? And we want to prove non-degeneracy at some ideal. Sorry, we want to prove that we want to prove non-degeneracy at some monomial ideal, and we can reduce to ideals of the form I delta, I sigma delta, which means, okay, let me simplify it. Can reduce two ideals of the form I delta, where delta is a subcomplex of sigma. Okay, so how does this look? Here's a particular case, right? If sigma is the suspension of a lower dimensional sphere sigma prime, then I sigma prime in a sigma is just isomorphic to the ideal generated by the North Pole and the South Pole. Okay, so I have my subcomplex, which is sigma prime, sitting in the suspension, right? And the non-phase ideal, right? The non-phases of I sigma prime, these are exactly these new vertices, right? See this and this. But I can have something else, right? I can have a triangulated sphere sitting somewhere. Somewhere in life and somewhere in space. All right, and then I have a subcomplex delta. And I look at I delta as an ideal in a sigma. And I can look at the pairing on that. Second reduction. Or pairing at, okay, so let me do it the following way. Let sigma prime, or I use sigma prime for something else. Let sigma tilde to sigma be a simplicial map, inducing homeomorphism of spheres. It's weaker, we don't need a homeomorphism, such that this map psi restricted to delta is the identity. So in other words, I have my delta sitting in my sphere. And now what I do, right, so this is delta sitting in my sphere. And now what I'm doing is I'm allowing you to modify the sphere anywhere. I'm allowing you to modify the sphere anywhere outside of delta. Okay, then non-degeneracy of pairing at I delta in a sigma is equivalent to the non-degeneracy of the pairing of I delta in a sigma tilde. Okay, so these two facts, right? So so this is a fact that I don't need to I don't need to really care what happens outside of delta. The second fact is up to such a subdivision of sigma, there exists a manifold. Let me call it, I usually call it, I usually call it a failing war compound. E for envelope in the subdivision sigma tilde, such that I E is isomorphic to I delta. Okay. the final observation, and this goes back, it's kind of going back. Well, I mean, there are two observations now. E has a nice decomposition. Meaning that it's combinatorially nice. You can build it out of simple pieces. I will not go into that, what that means in detail. But there's a second part here. So it's that IE satisfying pairing is equivalent to a Lefschetz property. On E. Okay, so we came full circle, right? We wanted to prove the Lefschetz property, reduce it to a pairing, and now what I said, okay, I find a new surface that contains my original delta, and I want to prove a Lefschetz property again. But the point is now I have these two together. This E has a nice decomposition. And I want to prove the Lefschetz property, right? And then now the trick is that we know how to prove the Lefschetz property for everything that has somehow a sufficiently nice decomposition. And that is it. Somehow, Lefschetz for a nice decomposition is easy. Okay, and that's it. Okay, and that's it. That's the idea for the first proof. And I want to give you the idea for the second proof. Idea 2. What we originally thought, or what Stavros and Vaso originally thought were differential identities. But now we kind of think that it's better to think about this in terms of a kind of Fourier decomposition and positive characteristics. So we call this possible identities. For the volume polynomial. Let me do it like this. And I will start to give you a little bit of an intuition what I mean by that. And then we will hear more about this approach in the next talks by I think there's more. First Vaso will talk in the afternoon, and then Stavros will talk next morning. Okay. So how does it work? Key is that we look at a ground field, and we look at, okay, so remember we want to look at this this linear system of parameters here, A of theta, right? So these A theta, I don't know what they are. They're kind of wild numbers in principle. So why not make them as wild as possible? Let's make them transcendentally independent. So, right, theta is of the form V delta times X, right? And this is some matrix, right? And this is some matrix, if you want to call it, or with entries theta ij, right? And now what do we want? Well, we want to look at these as independent transcendental variables and work with them like that. Of course, we cannot work over the original field because, I mean, they might not be in the original field. So what we do is we extend this theta ij. All right, we take the field extension by these coefficients, and that's it. So this is our new larger field. Let me call it K theta. Okay. This is a larger field. And now I will try to explain what the original, what the idea is of Stavros and Vaso, and then how this develops into a kind of beautiful into a beautiful theory. Okay. So the idea is the following. Idea. What we want to prove is that at no ideal, right? Remember, now at every ideal, I want the pairing to be non-degenerate. In particular, I want it at principal ideals. In particular, for all u in, okay, so let me for simplicity assume that the d is equal to 2k, d is equal to 2k, u in degree ak, theta, sigma, for all, yeah, there's some part of my screen that doesn't work anymore. Want that for all u in degree k, so equal exactly in half degree, that are non-zero, u not equal to 0, we want that u square in a d of sigma is non-zero. All right? And now here's the beautiful observation. There is a map from a d of sigma to the ground field. This map, I mean, this map we will explore tomorrow and today and tomorrow to a deeper extent. But this is, I mean, usually it's called the degree map. I don't like that name for this kind of lecture because we have several degrees. There are too many degrees today. All right, it's the monomials and polynomials of different degrees. So I usually call it the volume map. Again, this has a justification. If you think about it on the level, if you're a convex geometer and you're looking at this, then really you're looking at the volume, the mixed volume. So this is really just the usual valuation of the volume. So I'm looking at this map. And now I want to look at volume u square. All right. And remember, so this here, this is a rational function in the variables theta ij over the field K. So this here, all right, is also a rational function. All right, so here there are some there are just some monomials, right? But these monomials I've identified with the ground field. So this here in total is a rational function. So, or let me say, u square is some polynomial whose coefficients are rational functions, and volume u square is a rational function. Okay, so volume u square, this is a rational function. Okay. Okay, so now second trick. Idea. We want to look at some differential identity. We want to kind of prove that volume u square is not equal to 0. All right. Sorry, not equal to 0. And I have to remember to avoid that area of my screen. I don't know what happened. Want the volume u square. The idea is to define a differential operator, theta little sigma, sorry, partial little sigma, in such a way that volume u square is not equal to 0, right? If the differential of a rational function is non-zero, then the rational function is not. So what we want today, what we want to do is we want to define this differential operation in such a way that volume u square is equal to volume u times X sigma, and then we want to, I mean, just to make the degrees work out, right? So to make it homogeneous, I want to make it work out so that volume U times X sigma square is equal to this differential. That's what we want, right? Now, why is this useful? Because, okay, so sigma is of cardinality K, right? So why, if I have an identity like that, am I done? Well, I know Poincare duality tells me then Poincare duality tells me, or tells us all in the royal sense, tells me that U X sigma is not equal to 0 for some sigma. So if this is non-zero, then of course the volume, I mean, that's just the same thing, right? It's just evaluation. This is non-zero, then the square is non-zero, then this here is non-zero. In particular, this is non-zero. Okay. Next trick. Next, work over characteristic 2. Okay. Why is characteristic 2 useful? Well, so let's say U is equal to the sum of lambda I ui. Okay. And now I want to square this, right? I want to look at the square of this. So U square is equal to the sum of, sorry, I want to, sum lambda I xi, where the xi are small, the xi monomials of degree k, right? So now what happens? So the lambda i's are of course, wait, what are they? Well, they are rational functions in k theta. Right, they're rational functions in this over the original field k in the variables theta ij. So then U square is what, well, okay, so I'm in characteristic 2. So the nice thing is I have lambda I square xi square, right? All the mixed terms vanish. Next step. If I have some differential operator, delta sigma, right? So this is some concatenation of partial differentials, and I apply this to some function of the form lambda square f. Right? Then this is just the same as lambda square f, because, well, the differential of a square is just 0. Okay. So in order to find the right differential identity, right, to find sigma and prove the differential identity, we need only to prove it for monomials. Why? Because, right, again, I take the differential of U square, right, or volume U square, and that is, well, just the same as, okay, so volume, this is, let me write it down again. So this is the differential of volume of some lambda I xi square, and that's just the same as the volume of lambda I square xi square, which is just the same as, well, pulling out the sum. Right, I can just can do it even simpler. Sum lambda I square, and then I look at the differential of sigma of the volume of xi squared. Okay, and that's it. Okay, so now the question is, how do I define this? It doesn't really matter. So you can work out a specific identity. Let me not go over that because usually one forgets it anyway. And this is the key. So here, that's this somehow. Now finding this partial differential operator is easy. Okay, that's it. All right.